We have been hearing about Lorentz force magnetometers for some years. So as a topic of my presentation is quite similar to the previous one, I decided to do this thing to try to sum up most of the interesting data from the literature, starting from the basics of the operation of this kind of device, so looking at sensitivity, bandwidth, and noise, without neglecting power dissipation, which is always important for consumer applications, as you have just heard, and to try to compare all these results also with AMR and Hall effect devices. The fact that the previous talk was quite similar let me skip some background and some basics. You have just seen a Lorentz force device is basically based on a current which is pumped through some springs, and if the current is pumped at the resonance frequency, and if we have, for instance, in this case, a magnetic field directed towards the z-axis, we can have an in-plane motion which is amplified through the quality factor of the structure. And if you put like a differential parallel plate readout inside the structure, you can end up with an expression of the sensitivity here intended as the capacitance variation per variation of magnetic field can be rearranged in this way, which is actually my favorite way to look at the sensitivity of this kind of devices. It highlights an inverse dependency with the resonance frequency, which is therefore typically kept just above the acoustic bandwidth to be out of acoustic disturbance. Then we have some typical dependencies of the parallel plate readout, like the inverse of the squared gap and the damping coefficient per unit area. And you see the sensitivity improves with the device length and the pumped current, which are, however, for the pumped current, we have some constraints also related to power consumption. So a couple of more things about theory. Concerning the linearity, for instance, comparing this kind of devices with AMR devices, you see that the Lorentz force is intrinsically linear, and as typical displacements due to the Earth magnetic field are very low, we will typically not have mechanical nonlinearity. So the primary source of nonlinearity is just due to the capacitance, differential capacitance readout with using parallel plates. But if you just check the theoretical behavior with respect to the theoretical linear assumption, and you check the linearity error, this graph is taken for a typical configuration. We see that, for instance, we have 1% or 2% linearity error for displacements around 200 or 300 of microns, which from which you can find for a typical device the maximum magnetic field that can be read out within the 1% or 2% linear range. And you see that this number are quite large. Quite larger, for instance, than the typical magnetic field that you can measure, which is, as the previous author said, in the order of tens to 100 maximum of microtesla. However, if you look for applications like pedestrian navigation inside buildings, you can have very large disturbances in terms of magnetic field, and you want your sensor to be able to detect these disturbances and compensate them. So it's useful if the sensor does not saturate. So it's useful to have such large dynamic range for this kind of sensor, actually much larger than what you can get, for instance, with AMR devices. Concerning the bandwidth, as the device is operated at resonance, you just have the resonance frequency, which we have seen typically in the order of 20 kilohertz or a little more, divided by twice the quality factor, and this actually sets the limit to the maximum quality factor that you can have, as you need a bandwidth at least of 10 hertz. The bandwidth should not be that large in this kind of application, because typically the magnetometer is just used to compensate the errors accumulated by the gyroscope. So a bandwidth in the order of 10 hertz can be okay. So finally, an analysis of the intrinsic noise that you can reach with these devices. With intrinsic, I mean related only to the thermomechanical noise. We assume that we have a good electronics to read out this device. If you draw an expression for the signal-to-noise ratio, putting here the displacement that we have derived a couple of slides ago, here we have the power spectral density of the noise exerted in terms of force multiplied by the transfer function at resonance, and we can assume to have a filtering bandwidth which is equal to the mechanical bandwidth of the device. We can put this term equal to 1, rearrange some terms, and come to this expression of the minimum measurable field, which is actually the resolution that our system can get, which is here plotted in log scale. So for instance, this -6 is 1 microtesla, as a function of the sensing bandwidth and the log of the Lorentz current. So this is, for instance, 1 milliamp, 100 microamps, and so on. And what I did is I collected some data from the literature, some experimental results from the literature, to make a comparison at this level, starting from an earlier work by Emmerich dating back on 2000, and you see that effectively the predictions correctly matches their experimental results. You see that the marker crosses the surface. And the same for a couple of designs made by our group at Politecnico di Milano in collaboration with ST Microelectronics. The same for other devices. This is a work by the group of California Davis, University of California Davis, published recently on the Journal of MEMS, and previous work by the same group that exploited the parametric amplification of the equality factor still lies on the same surface. So we can basically say that if we look at the resolution, so the minimum magnetic field per unit bandwidth and unit power consumption, basically all these results are basically equal. So you can get a better resolution if you decrease your bandwidth. So for instance, you package your sensor at lower pressure, or if you pump a larger current. So for instance, you dissipate more power. And as the previous speaker said, basically the only work which is out of the surface, you cannot see the white marker because it's below the surface, is a work by Kinnareinen, and they basically exploited a slightly different process where you can deposit the metals on your device in like a spiral configuration, so that your current can recirculate multiple times on the springs. So basically, with a 10 times spiral, you get a 10 times improvement in your sensitivity. And indeed, if you multiply the results by a factor 10, we just come back on our surface. So this is basically what has been done so far. We go on analyzing this device, this particular device, which was designed by our group. The device design follows basically this design criteria. The first two ones are related to the fact that the sensitivity is basically independent on the number of readout sensing cells that you put here. Basically, in order, as the resolution improves with small masses, you can use basically the minimum number of readouts, of parallel plate readout cells that you want, and you get the same mechanical sensitivity, resolution, and so on. So we designed just two sets of parallel plate cells. The response frequency is just out of the acoustic bandwidth in the order between 20 and 30 kilohertz. In particular, for this device, is 28 kilohertz, and you can check. You can design your device so that at typical packaging pressures for industrial processes, you get a bandwidth, so a damping coefficient and a bandwidth that copes with the requirement. In this case, we ended up with 40 hertz of rate bandwidth. And this is a graph. The device is less than 100 microns in width times less than 900 microns in length. So it's a very compact device. These are some sample measurements of sensitivity with preliminary characterization using discrete electronics based on transimpedance stages. You see the two channels of the magnetometers are connected to these virtual grounds, and we measured, we put these devices inside the magnetic field. We swept the current at different frequencies, and to find out the resonance frequency of the device, you see for the two channel and then the differential readout highlighted here. Then we move it to a more precise setup formed by a 3-axis Helmholtz-Colt system, which is capable of compensating the Earth magnetic field and applying well-known values of magnetic field, so that we can calibrate the average offset of our devices and the sensitivity. We obtained an offset corresponding to less than 1% of the overall full-scale range, with a maximum linearity error which was lower than 2% over the testing range, which is between plus minus 400 microtesla. While the noise is currently limited by these resistors here, because the testing voltage was only 3 volts. If we were able to increase this voltage, we could have actually measured the intrinsic resolution of the device. So What we need now after the device is something about the circuit implementation, and in particular what is important is look for power dissipation not only in the device but also in the driving and sensing circuit. So we have made this kind of power budget by taking into account that the current dissipated by Joule effect in the springs can be let me say as low as 200 microamps, which is a value similar to the ones for which we obtained in the previous results. So this current is dissipated in the MEMS, which is here simply schematized as a resistance. Then we have some power which is required for the excitation circuit. Sometimes you might need some power in order to adjust the correct voltage level that you apply to have the current inside your MEMS device. If the resistance, for instance, if the resistance of this device is too low, you need to apply, in order to get a reasonable current, very low voltage values, and you cannot simply switch between the power supplies, so this requires some power dissipation here. And so we estimated a power dissipation of 50 microamps for an oscillator to keep the MEMS into oscillation. Then we have an analog front end, which is in this example format just by a transimpedance fully differential configuration followed by further gain stage, for which we will see a slide in a while. And some residual current can be dissipated further by the demodulation and ADC stage. With this power budget, we come to 350 microamps at typical biasing voltages of 2.2 volts for the selected real circuits. This turns into much less than 1 milliwatt per axis of power consumption. So it's an example of an analog front end we have developed, we are currently testing. As I said, formed by a full differential operational amplifier in a typical folded cascade configuration, which together with the output common mode feedback network takes up like 5 microamps, excluding the biasing network. With the biasing network, and assuming that we duplicate this stage for the following gain stage, we are in the order of 20 microamps of current dissipation, which is in line with the requirements that we had in our previous power budget. So what we can conclude after having had a look at the device and the readout electronics is that even if the intrinsic resolution of Lorentz force devices per unit bandwidth and per unit power consumption is still slightly lower, as this is a typical value, than state-of-the-art Hall and AMR technologies, we are quite close to them. And for instance, by an idea could be bringing the spiral path solution that was used by the paper referred in the previous slide by the group of Kinarainen to an industrial process which is not as complicated as it could see. We need just to put some metals on suspended parts. We actually have in the process metal on the same epitaxial layer, which is used to form the suspended parts. So with the shrink down of the this deposit metal dimension, we could get, for instance, 10 times improvements in the performance, which would put Lorentz force sensor below, in terms of performance, below the minimum resolution of Hall and AMR sensor. So that's it for the presentation of today. I thank you for your attention.